started. So, title of my talk today is Descriptive Complexity, which was, well, I mean, in some sense, we've been talking about complexity of evaluation of first-order formulas before. But I want to sort of hit on a couple of highlights about descriptive complexity today. So, as always, I'll start with a quick review of what we've seen in the past 3 lectures. So we looked at tools for establishing limits on the expressive power of first-order sentences and also first-order theories with a bounded number of variables, right? Essentially, we looked at 2 kinds of pebble games in the first lecture. In the second lecture, we looked at linking the expressive power of MSO to that of finite automata, which gives, on the one hand, tools for studying the expressive power of MSO. Like I showed you the simple consequence of proving that the Hamiltonian cycle is not definable, even on ordered graphs. And also limiting the complexity of MSO definable properties on decomposable structures. This was Courcell's theorem. Okay? And then in the last lecture, I looked at the complexity of first-order logic and sparse classes of structures using locality. So as I said, we've been touching on the themes of complexity. So what I want to talk about today is sort of one of the things that was one of the motivating reasons for studying finite model theory and ways of limiting the expressive power in the first place, and that is the fact that you can actually capture certain complexity classes in logical form. So the idea is descriptive complexity provides an alternative perspective on computational complexity. So classically in computational complexity, we measure the complexity of problems using resources, such as space-time on some machine model of computation. And when we talk of the complexity of a problem, the problem is formalized as a language that is a set of strings. Here we're going to aim at talking about the complexity of a class of structures, for example, collection of graphs, right? The kinds of things we've been talking about, and we're going to measure the complexity in terms of how hard it is to describe in a certain language. And of course, what's interesting is that the 2 are closely connected. So one thing I should say, I mean, I've talked about the evaluation problem for first-order formulas. I mean, Fagin also talked extensively about this. When we talk about complexity, and particularly now we're going to talk about the formal definition of complexity classes, formally defined as sets of strings, we really have to, at some point, make explicit how these structures get represented as strings. You know, we don't usually want to get stuck into the details of particular encoding, but it's good to fix it once, so I thought I'd put it down. Here's what I'll assume, for example. Fix a 3-letter alphabet. And if you have a structure, which is a universe with some number of relations, fix some ordering of the universe. Let's say A is enumerated A1 through AN. And then that ordering gives for each relation, any relation of arity k gets represented as a bit string of length n to the k. Basically, you take the lexicographical ordering of k tuples, and for each k tuple, you put down a 0 if it's not in the relation, 1 if it is in the relation. And so the string representing the structure is going to be a sequence of n ones to indicate the size of the structure. And then these bit strings representing the relations separated by these hashes. Now, the purpose of this thing over here is simply the case that if you have no relations, we still want the size of the string to be related to the size of the structure, right? That's why we write the size of the structure itself in unary rather than binary. So now, for any vocabulary whatsoever, the length of this string is bounded by some polynomial in n, and that's what we care about. Okay. One point to highlight is I define this string encoding of the structure A with respect to a particular order I chose on the elements. A different choice of order will give me a different string, possibly. Right? So it's worth pointing out that now we're thinking of a classical decision problem on strings. We're given a string for a fixed, let's say phi is a fixed formula, and the problem is given a string, decide whether it represents a structure satisfying phi. So this has the natural invariance property because the formulas are invariant under isomorphisms. I said this right at the beginning of the first lecture. We're concerned with properties which are invariant under isomorphisms. And so this isomorphism, of course, induces an equivalence relation on strings. Two strings are equivalent if there is some structure and two different orders which yield these two strings as representations of the same structure, right? So any language, any class of strings we're interested in is invariant under this equivalence relation. And this equivalence relation, now you can ask how hard is it to decide this, and this is of course just isomorphism. The graph isomorphism problem is what the complexity of this equivalence relation is. Okay. Having said that, I'm no longer going to worry about the actual details of an encoding of strings, having peeked under the hood, as they say, and we'll leave it there. Okay.
One question.
Sure.
You just mentioned, is it clear that graph isomorphism is equally complex as any tau isomorphism for any vocabulary?
Well, I won't answer the question. It's clear, but it is true. Right. It may require a bit of work, but to show it is the case.
Structure as a graph.
That's right. I mean there is a bi-interpretation to the language of graphs from many things, and that's easily computable. So
It's in this whole paper, the graph isomorphism is.
that's right. Exactly. I think important to say any vocabulary containing at least one binary relation, or at least one relation of arity two or greater, to be absolutely. Yeah. Okay. So this is a statement we've already seen a few times. It popped up in Fokion's presentation, and I mentioned it last time as well. For any first-order sentence, the complexity of the problem. So when phi is fixed, the complexity given a structure, and now by given a structure we mean given a string. Encoding it, decide whether it satisfies phi. We know is in logarithmic space and polynomial time. Now, this is already fairly low in complexity, right? But there are computationally easy properties in log space which are not definable in first-order logic, and we've already seen them. We know that you can't say, there's no first-order sentence which says that the size of A is even. That's clearly a problem in logarithmic space, well, in constant space, in fact. But it's not expressible in first-order logic. There's no formula, say, in one binary relation that defines the transitive closure. In fact, you can't express connectivity of graphs, even undirected graphs. And for undirected graphs, we know the problem is in logarithmic space. So first-order logic is strictly weaker than logarithmic space. If we go to second-order logic, all of these become definable. And I thought I'd just try and write down the definitions. We know it's all doable, but here's a formula of second-order logic that says that the size of the universe is even. What does it say? Basically says there is a binary relation B and a set S such that B is a bijection between S and its complement. All right. I'll leave out the interpretation of all of that, but basically that says that there's an even number of elements. And this is because B and S are quantified. This is a formula purely in the language of equality, which is what we want. Transitive closure. I already showed you in, say, monadic universal second-order logic, you can express connectivity, and this is just the same, except I now have constants A and B to say that there is a path from A to B, right? Or any set that contains A and is closed under the edge relation contains B. And I essentially showed you can't do this in existential monadic second-order logic. If you allow existential quantification over a binary relation, you can express this. And here was my attempt at expressing it. What does this say? It basically, I want to say there's a path from A to B. So I say there's a set P, and it's a set of edges, right? That's what this says. But I can't say it's a path in first-order logic. But these conditions, these are first-order conditions which guarantee that P contains a path. Okay? Basically, it says that well, there's an outgoing edge from P, an incoming edge from A, an incoming edge to B, and no incoming edge to A, an outgoing edge from B in P. For everything that has an outgoing edge, it's unique. For everything that has an incoming edge, it's unique. And everything other than A, if it has an outgoing edge, has an incoming one, and everything other than B, if it has an incoming edge, has an outgoing one. The only way you can satisfy all these requirements is if everything, from A, you have an outgoing edge, from B, you have an incoming edge, and any other point where there's something coming in has to have something going out. So P must be the union of a path from A to B, possibly with some cycles around, which loop everywhere. So these first order formulas don't rule out the possibility of these cycles, but if they're satisfied, there is a path from A to B. And so this says, that's what this says. Okay. Three colorability is another example I've shown you before. So all of this is motivating Fagin's theorem, which I suppose most of you have at least heard of. A class of finite structures is definable by a sentence of existential second-order logic, right? And all those examples I've just shown you, I mean, that was the reason for showing you could do this existentially, if and only if it's decidable by a non-deterministic machine in polynomial time, usually summed up by the simple equation. Existential second-order logic is the same thing as NP. Okay? If we want to make this, make a slightly more precise statement than that, given what I've just said, what we're saying is if you have a class of structures which are the models of some formula in existential second order logic, if and only if the collection of strings which code structures in S is a set of strings decidable in NP. Okay? In particular, note this set is always invariant under the isomorphism relation that I define. Okay. I know many of you could write down a proof of this theorem now. This is well known, but I'll just state the key points in one slide. In one direction, if you have a formula of existential second order logic, so in pre-next normal form, there exists some relations, and then theta for a first order formula theta, to decide whether a structure satisfies phi, given the input A, you guess an interpretation for these relations, right? So you just expand the string representing A with strings for these relations, and that's a polynomial amount of guessing. And then you just evaluate the first order formula, and evaluating a first order formula we know is in polynomial time, so the whole thing is an NP, right? That's one direction. In the other direction, we're given, let's say, a non-deterministic machine M, and are bound on its running time, which is a polynomial P. We write down a formula which basically says there is a binary relation which is the linear order of the universe, and then there exist relations, and you have to sort of do a bit of coding here, which code an accepting computation of this machine M of length P, which starts with the coding of the structure. Now, of course, the way I've written it, it looks like this formula depends on the structure, but of course that's not what it means. It's you write down the axioms which ensure that when this is interpreted in a structure A, what it is saying is that the initial state represented by these relations on its tape has exactly the representation of the structure in which it's interpreted. And the point is, again, because the length of the computation is bounded by a polynomial, this can all be coded in relations of fixed-arity, and you just have to state that, in first order logic, that from, one time instance to the next, it's a consistent computation. Small remark about this invariance under the order. This machine M, clocked by the polynomial P, might not define a set of strings which is invariant under the order, under this isomorphism relation. So this formula doesn't define the set of strings accepted by M. This formula defines the set of structures for which there is some order which results in a string that is accepted by M, right? So if you take this, translate it into this, and then translate back into a machine, you don't necessarily get the same set of strings. You get its closure under the isomorphism relation. Okay, but that's okay. I mean, this is sufficient for proving the theorem. Okay.
Which was proved not far from here. Ron Fagin was a graduate student in the math department.
In the math department over here, yes, in 19. Well, I mean, I guess the thesis was 73.
72.
72. Okay.
But if you already talk about credit, I think Fagin is overcredited for this. You should look at my spectrum survey paper on the history of all this.
Okay. No,
John Selman,
John Selman.
in Zurich, and they were. It's true he formulated it succinctly, but I to give only him the credit, I think is
Okay.
overdoing it. He deserves it, but it's overdoing it.
Okay. We're. I mean, I have to admit that there's lots on my slides which is uncredited. I mean, I'm treating this more as a, as course material. So I think we leave discussions of credit for the break. Okay. The question that follows, and which motivated a lot of work, which I'm going to talk about in the rest of the talk, is can we do something similar for the class P? Okay. So Chandra and Harald posed this question in a paper in 1982. And it remains, as I said, a major open question in descriptive complexity. Can we find a logic for polynomial time in exactly the sense that for any class of finite structures, it's definable in L if and only if the set of strings that encode it is decidable by a deterministic polynomial time machine? Okay, now, what is a logic L? I mean, as I said, Chandra and Harald asked this question. And the feeling is, if you could come up with a logic L, we would recognize it as such. But maybe the answer is negative, and what would it mean to give a negative answer to this, right? And Gurevich formulated what a negative answer to this question would be and conjectured that it is, in fact, the case that there is no logic. So formally, just said loose, I mean a very loose requirement, the logic L should be a recursively enumerable set of sentences with a computable map that takes each sentence to a pair which is a deterministic Turing machine and a polynomial bound on it, such that running this machine to that bound actually accepts a class of structures. In other words, it's invariant under the equivalence relation of structures. So we require that, and then of course we require that for every polynomial time property there is a...
Historically, I think it's the other way around. The second question was what Chandra and Harald asked, and you reformulated in the version of a logic.
Well, no. I think what was missing from the Chandra and Harald formulation was precisely this idea of a computable map to pairs of machines. They asked the recursive enumerability, but
they didn't formulate as a logic.
No, I know, that's right. But I mean, I think this notion of a computable map to a pair is crucial to make this. I mean, in Gurevich's paper, he explicates many slight variations and so shows that many of them can be trivially answered. And this is the one that's the key. Okay.
Gurevich conjectured that this is not possible. So in other words, he was implicitly saying there's no
logic for P. That is Yuri's conjecture, formulated in here, that there is no logic for P, and so in particular P is different from NP. I mean,
not just that, but that graph canonization is not in polynomial time.
That's true. Yes.
So he actually believed that
at the time.
Okay.
Well, I don't know. Yes. I mean, I still think this is plausible, right? It's
Okay.
right.
Okay.
So what do we know about the existence of a logic for P? I mean, the interesting work here starts with fixed point logics, which Fokyon has sort of introduced in the form of, data log, which is the closure of existential positive first order logic under fixed points. Classically, I think was it A.O. and Ullman who proposed a fixed point logic as a database query language extending first order logic with fixed points.
It was actually again Chandra and Harald. I mean, they suggested you should have a logic express transitive closure.
Oh, okay.
The 79 paper.
79 paper. Okay, but so rather than least fixed points, I'm going to talk about inflationary fixed points, which gives you an equivalent logic. So let me just formulate it. So suppose we have a formula, first order logic, in a vocabulary which contains a carry relation R, right? And let's say this formula has three variables, among x1 to xk. We associate on a given structure A, which interprets all the relations other than R, so it's a sigma structure. We think of this formula as defining an operator which, given a carry relation, defines another one, right? So it takes a carry relation, plug in an interpretation for R. This formula then defines a carry relation, right? And we call that phi of R. Okay, so it's a map from carry relations to carry relations. Now, we'll define the following non-decreasing sequence of relations on A. Start with the empty relation, and at each stage, take the relation you have defined so far, plug it into this operator, and add it to what you had before. So take the union. This is the inflationary nature of the operator. So it's an arbitrary operator, but we make sure the sequence is non-decreasing by just taking all the tuples we define and adding it to what we have so far. And we call the limit of the sequence the inflationary fixed point. Because this is a finite structure, this limit is reached at a finite stage, to be precise, at most n to the k, if there are n elements of A. I say it there. Okay. And so we form the logic of inflationary fixed points, which I'll just call FP, by adding an operator which allows you to define this relation, basically. So if you have a formula for vocabulary sigma union R, there's an operator IFP which binds the relation symbol R, and which basically defines the relation, which is the inflationary fixed point, and then you can construct a formula which says some tuple is in that relation. Okay. If instead of inflationary fixed points, I had restricted these formulas to be, say, positive in the formula R guaranteeing their monotone, I could take the least fixed point and I get something similar. But it's basically, this allows me to avoid this syntactic restriction to positive formulas. And it is known that in terms of the expressive power, the two logics are the same, whether you add least fixed points or inflationary fixed points. This was shown by Gurevich and Schiller back in '86, specifically for finite structures. And then Kreutzer showed that even if you allow infinite structures, this is still the case. Okay. So that's the logic of fixed points. And now here's just as an example, take the classic inductive definition, transitive closure. And here's a formula which defines the transitive closure of a binary relation. I suppose strictly speaking, it's the reflexive and transitive closure that I've defined over there, because as the base case, I take x equals y. Okay. So, so the expressive power of fixed point logic properly extends that of first order logic. This already demonstrates that. You can easily now define that a graph is connected. And I think in Fokion's lecture, we saw a data log definition of graph two-colorability, or graph non-two-colorability. But because this logic is closed under negations, we easily have a definition of graph two-colorability, which was another example we saw is not definable in first-order logic. It's still the case that every property definable in this logic is in polynomial time, because, as I said, any inductive definition closes in at most n to the k steps, and each step involves the evaluation of a first order formula, which can be done in polynomial time. Well, as you allow nested inductions, it's not necessarily a first order formula, but still, by induction, every property you can define is computable in polynomial time. Okay, I've already said this. And what we know is that if you restrict yourself to structures which include a linear order, that is, they interpret a linear order, there's a binary relation which is a linear order of the universe, then every polynomial time property can be expressed in this fixed point logic. And the reason is this. Recall my quick one-line statement of the proof of the difficult direction of Fagin's theorem, the non-trivial. Well, I don't know if either one is trivial, but anyway. I said, from a non-deterministic machine and a polynomial bound P, we construct this existential second-order sentence. Now we're starting with a deterministic machine, And we don't have to say there's a linear order because one's already given to us. So we can drop this. And then if the machine is deterministic, you can show that all the relations that code the computation can be defined inductively because there's a single computation. And the relations which represent it have a simple inductive definition. And so you get the translation into fixed point logic. Okay? But you can't, I mean, this restriction to a linear order is important. You can't get rid of that. You can't build up the linear order inductively. And this is sort of what Kusha was referring to. Because it's an open question whether you can come up with a canonical string representation of a structure in polynomial time. Whether there's a way of constructing an order in a canonical fashion by any polynomial time algorithm. If you could, then we'd be done, in a sense. If you could, then we have a logic for P in the Gurevich sense, and we also have the, for example, graph isomorphism is then in P. If you can't, then P is different from NP, right? So either of these looks like a hard problem to solve. But that's, of course, that doesn't preclude the possibility that you can prove there is a logic for P by some other means, right, without the canonical string representations.
Now we know it's quasi-polynomial, right?
Canonical string, yes, constructing is quasi-polynomial thanks to Babai's.
Actually, does it only give isomorphism or also canonical labeling? I mean, his
Babai's thing,
yeah.
It gives canonical labeling. You can, yeah. So, sorry?
Can you now make explicit what Babai gives?
So,
Acoustically, I didn't hear all of it.
no, I just Babai's result tells us that there is a quasi-polynomial algorithm which will construct a canonical representation. Okay. Yeah, that was it. That was it. Okay. I'll skip this remark. I don't think this is. Well, maybe I'll say it. So here's one way of thinking of it. Take all sentences of fixed point logic which may refer to an order, which is not interpreted by the structure, right? But which are invariant under the choice of order, which means on any given structure, whatever order you choose, either the sentence is true or the sentence is false. This collection of sentences is, in some sense, a logic for P. Every polynomial time property is expressible and nothing else is. But it's not a recursively enumerable set of sentences, right? Because this invariance property is, well, undecidable and strongly so. But if you restrict yourself to fixed point logic itself, right, those sentences of fixed point logic which don't refer to this order, then it's too weak to express all properties of P. Why is this? You can't even express that the number of elements in this structure is even, right? The most trivial property that I said is not first order definable. And this takes us back to, I introduced finite variable logic in the first lecture, right? Remember LK is the first order formulas using only the variables x1 to xk. And now if you look at the inductive definitions, if you start with a formula which has k variables altogether, then it turns out that each of these, phi 0 and then phi 1, phi 2, each of these as a relation, I mean is definable by a sentence in L2k. So a first order sentence, or first order formula I should say, with 2k variables, will define phi m on all structures. And the proof is an argument by induction on the structure of the formula. Basically, phi 0 is the empty relation everywhere, so that's easy to define. To define phi m plus 1, you take the formula phi, which we know has k variables altogether, and you replace all instances of r by the definition of phi m. You have to do a bit of renaming of variables to avoid capture, but the key point to remember is still no subformula contains more than 2k variables at any point, whatever the value of m is. And that was the key point I said about limiting the total number of variables. So you can rename variables to get it down. So this means that if you fix the size of the structure n, this formula, which is equivalent to then phi n to the k, is definable by a formula of L2k. So the number of variables here doesn't depend upon the size of the structure. That's the key point. Right? You can, for any fixed size, you can translate it into a first order formula, and the number of variables doesn't depend upon the size, which means, put another way, for any property of fixed point logic, we can find a k so that the formula is invariant under k equivalence. It's another way of saying it is you can actually turn this formula into a theory in LK. It's equivalent to a theory in LK, an infinite collection of LK sentences. And we've already shown that evenness is not definable with a fixed number of variables. We saw that with a pebble game in the very first lecture. So evenness is not definable in fixed point logic. We saw the existence of a perfect matching in a graph is not definable. We saw Hamiltonicity is not definable. Now this seems less surprising. This is an NP-complete problem. You wouldn't expect it to be definable. But we actually can prove it's not definable. We don't need to assume that P is different from NP to prove it. This is just the case. Okay. Now, all of these results, all of these inexpressibility results seem to involve some form of counting. Well, I say some form of counting. These are not counting properties. This is a property which is about counting the size of the structure. But the examples that we use to prove that perfect matching and Hamiltonicity are not definable all turn out to be simple counting examples, which is kind of what led Immerman to, back in the 1980s, to suggest we extend fixed point logic with a mechanism for counting, and maybe that would give you all of polynomial time. So what is the extension? Let me define it quickly. So our logic has two sorts of variables. So what I'm going to present is not necessarily Immerman's original definition. It's tweaked slightly. I mean, over the years it's been made a little bit cleaner. We have two sorts of variables in our logic. One ranges over the domain of the structure as before, and another which ranges, say, over the non-negative integers, right? If we have a formula with a free variable x, and now x can actually be a formula of a variable of either type, we can form a term which refers to the number of elements in A which satisfy. So the number of elements, x, such that phi is true of x. Okay? This is to be interpreted as the number of elements. So we have variables which ranges over numbers. We have terms which range over numbers. On number terms, we have arithmetic operations. Now, on the face of it, this is getting far too rich, because we have just thrown in all of first order arithmetic, it seems, into our logic. So we'll limit quantification over number variables. So this really should be a new. So you don't have unrestricted quantification over numbers, because that would take us well beyond polynomial time into the realm of the undecidable. But so any quantification over numbers has to be bounded by a term. Okay. In Immerman's original formulation, these things only ranged over numbers up to the size of the structure, but it seems, this allows you to let them range wider, as long as it's every quantifier is bounded, and then you can show that the expressive power entirely stays within polynomial time. Okay. So fixed point with counting, as I said, at one point it was suggested that this might capture polynomial time. It's not, it doesn't, and I'm going to sort of tell you why. To analyze this, it's useful again to go back to first order logic and consider an extension of first order logic with counting, rather simpler than the one I just presented. We don't have two kinds of variables. Instead, we'll have, for each fixed value I, fixed positive integer I, a quantifier which says there exists I elements x such that phi. Okay? But at the same time, like we did with LK, we are going to limit ourselves to the variables x1 to xk. So note, this logic ck as defined is actually a fragment of first order logic. You can translate this into a first order formula just by expanding this into I individual quantifiers. But the problem, it's the combination of the two. If you do that, you blow up the number of variables. So ck is certainly not a fragment of lk. Ck, even for fixed values of k, is not a fragment of lk prime for any k prime, right? The translation doesn't you can't translate with a bounded number of variables. But it's a well-defined fragment of first-order logic. And therefore, we can define the notion of equivalence in this, and it is still a coarsening of elementary equivalence. So this is another stratification of elementary equivalence. Okay? Because this is a fragment of first-order logic, and we say A and B are equivalent with respect to formulas that appear in here. And then what you can show is every formula of fixed point with counting as defined on the previous slide, for each such sentence, there is a k, such that it's invariant under this k equivalence. This is, again, the same idea. You unfold the inductions by substitution that keeps the number of variables bounded, and then you have to sort of get rid of those number variables using these counting quantifiers instead. And it's rather more work, which I'm not going to do at the moment, but this is it. And so this elementary equivalence relation, this stratification of elementary equivalence, is our tool for showing limitations on the power of fixed point with counting. Okay. So FPC was proposed, as I said, by Emmerman, but already in I suppose 1989 was the first version of this paper. This refers to the journal paper. Pfeiffer and Emmerman showed that there are polynomial time properties of graphs that are not expressible in fixed point with counting. Okay, now it's not, there isn't a succinct statement of the polynomial time property they show is not definable. But the construction enabled a number of other results to follow. Okay, and the one I'm going to focus on is this one, which appears in a paper by, Albert isn't here at the moment, but anyway, Albert, Andrei Bolotov, and myself, which showed, in some sense, a rather natural problem in polynomial time. The problem of solving linear equations over the two-element field is polynomial time solvable but not expressible in fixed point with counting. There are other things, for instance, on my list of 3 examples of things not definable in fixed point logic, I had evenness, perfect matching, and Hamiltonicity. Evenness becomes trivially definable once you've thrown in the counting. Perfect matching, it turns out, the existence of perfect matching is definable. This is not a straightforward result, but one I'll look at tomorrow. Hamiltonicity, you can still prove, is not definable in fixed point with counting. But that's something I'm not going to get into. There are other things like 3-colorability, which you can prove are not definable. But OK, just as an illustration of the methods used, I'm going to focus on this one. OK? So this is clearly solvable in polynomial time. Yes, Sam?
Actually, don't mind backing up a slide or two. You're saying that the quantification over constant integers I in counting is the same as the number operator.
Well, I'm not saying it's the same, in the sense that if you added these to fixed point logic, you would get something weaker. Because in any formula, you would have only finitely many of these constants occurring. But this equivalence relation basically is over all formulas. And so you have an infinite set of integers. And what you can do is you can show that a formula of fixed point logic can be unfolded into this sort of infinitary thing using just these constant quantifiers.
So you could express things like majority.
That's right, but with an infinitary, with a theory effectively, with an infinite set of sentences.
Oh, okay.
Right? And
I'll have to process that a little bit.
Okay. Right. So this is polynomial time solvable by means of Gaussian elimination, and now we aim to show that it's not in fixed point with counting. Let's see. So first of all, what do I mean by a system of linear equations as a structure? So I'm going to take my structures to be of the following form. We have the universe is going to be the set of variables and a set of equations. Okay, that's the universe. And now every equation is basically for some set of variables it's going to be the sum over S let me put it this way, sum over x and x is either 0 or 1, right? So every equation is just sum over some set of variables with a 0 or a 1 on the right-hand side. So I'll have a unary relation for those equations which have a 0 on the right-hand side, another unary relation for those equations which have a 1 on the right-hand side, and a sort of the matrix, if you will, which says that the variable x occurs on the left-hand side of equation E. Okay? So one binary relation, two unary relations. And that's my system of equations. And now I have the class of structures which represent solvable systems is a well-defined class of structures. And I ask, can I define this in FPC? I'm going to prove you can't. And it's clearly polynomial time decidable, because you just write this matrix out, do your usual Gaussian elimination, and it gives you the answer. So to show that you can't do this in FPC, what do I need to do? I need to give you for each k two systems of equations, one of which is satisfiable, the other isn't, but they cannot be distinguished in CK. Right? I want to give you such a pair for each value of k. And that'll prove that you can't do this in FPC. I mean, this property of being solvable is not invariant under k equivalence. Okay. So there are two things to do. First of all, I'll tell you what these systems of equations are. And then we'll look at what tools we have for proving k equivalence. I mean, we're going to need variations on these pebble games we had before. So I'm going to start with a 4 regular connected graph. You'll see the reason for the 4 before. It's actually not, you can get away with 3, but take a 4 regular connected graph. So every vertex has 4 neighbors. And from this I define, I thought I'd fix these g's anyway. I define a system of equations where the variables, the set of variables, consists of the set of edges in the graph with 2 variables for each edge. So I have twice as many variables as I have edges in the graph. Right? So I'll call these variables xe0 and xe1 whenever E is an edge. My equations for each vertex V, let's say a vertex V has 4 edges incident on it. I mean, every vertex V has 4 edges incident on it. Let's say E1, E2, E3, E4. I'm going to write down 16 equations associated with that vertex. And basically, these 16 equations are given by this. I take from each of the edges one of the 2 variables. That's my 16 choices. And I say the sum of them is, what I put on the right-hand side is the sum of those subscripts modulo 2. Okay? So, okay? Prakash was looking slightly confused, so I paused. You're happy. Okay. So this is a set of 16 equations associated with each vertex V. That's my system of equations, EG. Now, from EG, I define a different one, which I'll call E tilde G, which is exactly the same, but I pick one vertex, V, at random, and for that vertex, I change all the 0s to 1s and all the 1s to 0s on the right-hand side. Okay, so I add 1. That's my system E tilde G. And the claim is, first of all, that this original system is satisfiable. The second one isn't. And then I'm going to show that these, if for a suitably chosen G, and I'll have to explain to you what that is, these things are going to be indistinguishable in CK. So first of all, let's establish these claims about satisfiability. Why is this satisfiable? EG is satisfiable for the rather simple reason that I just set each variable to the value of its subscript. And then obviously all of these equations are satisfied. Why is this system unsatisfiable? Well, I'm just going to give you a subset of the equations which are already inconsistent, and therefore the whole system is satisfiable, and that's those in which the only subscripts are 0. So basically pick one equation from each vertex, the one where all the subscripts A, B, C, D are 0, right? Then all the right-hand sides are 0 except 1. Okay? All the right-hand side, but if you sum the left-hand sides, every variable occurs twice, because each variable is associated with an edge, and that edge has two endpoints. So every variable occurs twice. So summing all of these gives you 0, modulo 2, but the right-hand sides add up to 1, because they're all zeros except for exactly one occurrence of 1, and therefore the system is inconsistent. Okay? So we have a satisfiable system and an unsatisfiable system. And now we want to show that for each k, we can find a graph G which makes these two CK equivalent. And actually, I mean, on my slides, I've tried to do this all explicitly, but actually it's sufficient, interestingly enough, because this is a concept that has appeared, it's sufficient that the tree width of G is bigger than k. Right? I said it's 4 regular and connected to define the system. If the tree width of G is bigger than k, then these things are indistinguishable in CK. And this, okay. We'll get to the construction of G in a moment. How are we going to prove that they're CK equivalent? We want a pebble game. And there is, if you looked at the pebble games we defined, there were natural moves for each, for the existential quantifier, right? Existential quantifier and universal quantifier. You pick elements in the two structures. Immerman and Lander defined a pebble game for CK. By the way, how many of you know Lander?
Well, he was the head of the
Eric Lander.
Human Genome Project.
Exactly, yes. Yeah, so, I think also served on the Presidential Scientific Advisory Committee for Obama. And so, anyway, this is not the result which got him that appointment. Anyway, so they defined a pebble game for CK equivalence, right? So again, we have spoiler and duplicator, and we have k pairs of pebbles. Okay, and now we want to move corresponding to these counting quantifiers. So think of it. Essentially, we have, there exists I, x, such that phi. And let's say spoiler is asserting that this is true in one structure and false in the other. How do we do this? Spoiler picks a value of I. Sorry, no. Let's call this M. Okay. So here, spoiler picks I means spoiler picks one of the pebbles. That's why. Okay. And a set of elements of one structure. So basically, say spoiler is asserting this is true in B, so pick a set of elements that satisfy this. Duplicator has to respond with a set of elements of the other structure of exactly the same size, saying, well, there is a set in the other set on the other side which also has this property. Now spoiler says, aha, you cheated. You included something that doesn't satisfy phi. So spoiler picks an element of the set that duplicator chose, and duplicator has to respond with an element of the set that spoiler chose and says, ah, but this one looks just like it. And then the game moves on. So at the end of the round, only 2 elements have been selected, but the process of selection involves choosing these sets, and they have to be the same size. Okay? I present this because, presented this way, it's kind of clear that it captures this sort of semantics of this quantifier. I is one of these pebbles. At any point, spoiler can move any one of the pebbles. I ranges from 1 to k. Right? There are k pairs of pebbles.
But in the sequel of the game, what is the role of I?
Spoiler chose which pebble spoiler is going to place, and then places that AI on an element of X, and duplicator has to respond with BI. Okay. Right, so this is the usual kind of connection. This is, I mean, in the Theorem original construction, this was the game they used, but actually it's more convenient to describe in terms of a bijection game defined by Lauri-Hella, which is as follows. It's kind of, again, we have 2 structures, k pairs of pebbles. Again, spoiler chooses I, the pebbles that are going to move. And duplicator has to respond by giving a bijection between the two structures, right? In some sense, basically stating for every possible move what the response will be in one go. And the bijection has to respect the positions that are already pebbled. So for everything other than I, HAJ, you know, of the currently pebbled position is respected by this bijection. Spoiler then chooses some element of the structure, and the pebbles go on that element and its image under the bijection. Okay? And if this thing is not a partial isomorphism, duplicator loses. This, on the face of it, looks much harder for duplicator. having to give a bijection is having to respond to all possible moves. But it turns out to be the same. Duplicator has a winning strategy if and only if the two structures are CK equivalent. And very quickly I can tell you why. Clearly, if Duplicator has a winning strategy for the bijection game, then there's a winning strategy in the counting game, because whenever spoiler chooses a set, you just look at its image under the bijection, and that gives you a set of the same size in which Duplicator can play. For the other direction, what you do is you look at the equivalence on elements induced by the CK equivalence. So you have the structure A, you have the tuple of currently pebbled positions. You say that two elements are, sorry, what have I?
Something's missed with the I. How is the I quantified?
No, okay. So the point is, I'm assuming Duplicator has a winning strategy in the counting game, and I want to show the winning strategy in the bijection game. So look at one move. Spoiler chooses I, and then what Duplicator does is look at the following equivalence relation. Namely, look at the currently pebbled positions, and look at what substituting. If substituting A for the ith position and A prime for the ith position result in CK equivalent positions, we say these two things are equivalent. Basically, these two moves, are equivalent as far as the game is concerned. For each of these equivalence classes, by the assumptions of the counting game, Duplicator has a response which is a set of the same size. And then you stitch these sets of the same size together to construct a bijection between the two. And that gives you can show that that's a winning move in the bijection game. Okay. So this is the tool for showing two structures are equivalent. Remember what we're after. There was these systems of equations we constructed from a graph. Now I said that the graph has tree width at most. The assumption is the graph has tree width at least k. And what I'm going to use is a characterization of tree width in terms of cops and robbers games. I'm not going to tell you why this is characterization. I'll just use the cops and robbers games, and I'll just show you an example of a graph where this works. So you don't need to know its equivalent, but it's just an interesting fact. So the cops and robbers game is the following game. We have an undirected graph, and we have two players, a cop player and a robber player. The cop player controls a team of k cops, and the robber controls a robber. At any given point, so the robber player controls the robber, let's say, yes. At any given point, all these k cops and a robber sit on vertices of the graph. What does one move consist of? So the cops are sitting on some set of at most k vertices. Robber is on some vertex r. The cop player chooses some set of cops which are going to move and announces the position they're going to move to. Okay, and the move, these cops have helicopters. They just fly and land anywhere else on the graph. Right? They're not constrained by the graph structure at all. They're going to move. The robber is constrained by the graph. And the robber can move from the current position to any position as long as there's a path from R to S, not just one step, any path. But the path must not go through any of the stationary cops which are acting as guards. Okay? This leads to a new position. The robber is now in position S, and the cops are now basically in all the ones that didn't move plus the new positions.
Sorry, in the middle thing, the path is allowed to go through the Y vertices.
Yes.
Okay.
Go through them, yes. So
but obviously, if it sits on them at the end, then it's...
That's right. If a cop and robber end up on the same node, the robber is caught and the game is over. Okay. So the point is, I don't know if I think I have it somewhere on the slide, but it's worth mentioning now. This is a characterization of tree width, right? In the sense that if you can show that a graph has tree width greater than k, if and only if robber has a strategy for winning against a team of k cops. Okay, basically, if the graph is sufficiently interconnected, the robber has a strategy for avoiding k cops. There are always paths. So I'll give you just an example, because all I need is one such graph. And the graph I chose is the k by k toroidal grid. What do I mean by this? I mean a grid which is k by k. And by toroidal, I just mean we also have edges which go around. So think of this as embedded on a torus. And notice this is 4 regular, which is why I chose 4 regular graphs at the beginning. And once you have a k by k grid, this has tree width greater than k. More to the point, I can show that explicitly the robber has a winning strategy in the k cops and robbers game. Why is this? Suppose at any given position, the cops are sitting on a set of x of vertices, on a set of at most k vertices, right? And I argue that the graph that remains when you remove those x contains a connected component with at least half the vertices. Okay, why is this? Well, if all the vertices are in distinct rows, then removing them just leaves a connected graph, right? Because, you remove one node from each row, you can always get around to every point in the row, and so on. So if they're not in distinct rows, then there is at least one row, right, which contains none. So it's connected to every column, right? And it contains, in at least half the columns, k minus 1 vertices in its connected component. Because to disconnect the whole column, you need 2. So you can disconnect at most half the columns from it. Okay? And that's it. So if you remove k vertices, there's always a connected component with at least half the vertices. And now Robert's strategy is simply described: stay in the big component. Right? So I had mentioned to you when I talked about tree width that the grid, has tree width minimum of its dimensions, and I gave you sort of an upper bound by describing the decomposition. This is how you show the lower bound. Okay, right, and we're kind of done now. Well, nearly done, right? Stay
in the large component and avoid the y's, right? I mean, somehow.
Well, no. So the point is, at any point, some of the cops are moving. And you know where they're going to land, right? So the large component in the previous move and the large component in the next move must overlap, right? So you can move, there's a path from the current position into the overlap. You go there and stay there. Okay. So I mentioned this, the cops and robbers game actually characterizes tree width. So it would have been enough to just say we're taking a graph of large tree width. And now what does this have to do? So now I want to claim that once you have this, we're going to combine the robber winning strategy, right? We're going to turn the robber winning strategy in G into a winning strategy for duplicator in the bijection game played on these two systems of equations we constructed from G. And the idea is this. At any point, we have k pebbles placed on these two systems of equations. And let's say a bijection between these two systems is good, bar v, vertex v in the graph G, if it's an isomorphism everywhere except for the variables and edges incident on v. Sorry, for the variables which correspond to edges incident on v. So the point is, remember, we constructed these two systems of equations which were the same except for at one vertex. You can define an isomorphism, which is a map, a bijection, which is an isomorphism, except at that one point in the graph. Let's call that a bijection which is good bar v. You can show that if you have a bijection which is good bar v and a path from v to u, then you can construct a bijection which is good bar u, so isomorphism everywhere except around u, by changing the bijection just at the vertices corresponding to the path from v to u. So this idea is simple. If the bijection, as it were, the inconsistency in the equations is at a certain vertex, and you have an edge, for the two variables that correspond to this edge, you interchange the 0 and the 1. That makes it consistent over here and inconsistent over here. And you can repeat this process along any path, right? And now, in the bijection game, duplicator plays these bijections that are good except at a single vertex, corresponding to the current robber position in the cops and robbers game. So basically, we're playing this bijection game. Duplicator on the side has a copy of the cops and robbers game, and where the pebbles move, treats that as a move by cops on this, finds a path for robber to take, and changes the bijection along a path, makes no changes where the pebbles actually appear, because that's what the robber strategy guarantees, and the inconsistency between the two systems is always hidden at a position where there are no pebbles, because that's what the cops and robbers game guarantees. Okay? Okay, I'm running out of time, so that's it for this proof. And let me just sort of say a very quick survey of other work in this area. It turns out now, fixed point with counting, so it's not all of polynomial time by that proof we just gave. It turns out it's incredibly powerful. Already Immerman and Lander showed that all properties of trees, polynomial time properties of trees are in there. It's extended to all graphs of bounded tree width. Any property of graphs of bounded tree width in polynomial time can be expressed in FPC, which already explains why we had to use unbounded tree width graphs in our proof. In fact, FPC captures P on the class of all planar graphs. And this sort of stunning result, I say 2010. I mean, of course, this is still in the course of publication because the proof is a 450-page monograph. But on any minor closed class of graphs, fixed point with counting captures all polynomial time properties. And on all of these, the proof essentially proves that you can construct a canonical ordered representation of a graph in the class, and that can be done in fixed point with counting. So not just in polynomial time, but in fixed point with counting. And yeah.
It sort of begs the question, what about these nowhere dense graphs? So what's known about?
Not the bounded degree.
That's right, exactly. So this construction already gives you a bounded degree class on which it fails. Yes.
I see.
Yes. So.
3 shows that you have to use the toroidal graphs?
No. Because, I mean, when I convert the so I start with this graph, and then I turn this into systems of equations. You could encode those systems of equations as graph gadgets, which is what sort of Cypher and Immerman originally did. And that doesn't preserve the topological properties at all. So in fact, even though you start with a toroidal one, once you do the gadgets, the class that you get doesn't exclude any minors. You can show that. In fact, it would contradict this.
So what's the meaning of the third statement on planar graphs?
So any property of polynomial time property of planar graphs is expressible in fixed point with counting. Just that.
Your equations are not?
They're definitely not planar. I mean, if you turn them into a graph, or if you look at the Geisman graph of these equations, it's definitely not planar.
Okay.
Right? Okay, and so my last slide, I wanted to say, so what can we add to FPC while remaining inside P, now that we know that FPC is a proper fragment of polynomial time? We've looked at logics with matrix ranks, a rank operator or finite fields. This is actually, in some sense, specifically designed to address the one problem we know, the systems of linear equations. If you had an operator for computing the rank of a matrix, you could express that. So it's clearly strictly more powerful. But so what? Maybe a more interesting one is this choiceless polynomial time, defined by Andreas here, along with Yuri and Sara and Shella, which is, it's based on a machine model rather than a logic, but it satisfies the Gurevich criterion for a logic. Okay? The idea is a machine model that works directly on a relational structure rather than on strings. And this class is then the polynomial time and space restriction of these machines. Both of these can, fixed point with rank and choiceless polynomial time with counting can be proved to be strictly more expressive than fixed point with counting. But their relationship to each other and their relationship to P, I think, all remain open questions. We don't know that either of these includes the other. We don't know that either of them is properly included in P. what we need is new tools for analyzing the expressive power, you see. So we've been building up from tools for first-order logic, fixed-point logic, fixed-point width counting, and here we are now in new territory. Okay, and this is where I want to stop for today. Questions?
Just to make sure I'm not mentally oversimplifying something. In these systems of equations,
Yes.
The structure actually has the variables and the equations as
That's right.
individual elements. But in the duplicator strategy, nothing ever happens with the equations. He's just
Well, of course, spoiler can put a pebble on an equation. And since an equation corresponds to a vertex, you go back and put a robber on that vertex in the graph, and it still works, right? I mean, I could have, because I limited it to 4 regular graphs, I could have just put in just the variables as the universe and encoded all the equations into relations. I gave the general form because actually, at one point I was thinking of writing the general argument with an arbitrary graph, with not of bounded degree and so on. But
Is there a formal, a more general connection between the Hobbes and Roberts game and the K-pebble bijection game? One is played on one graph, the other is played on 2 graphs, but if you do something like some sum or product on the graphs, is there some general result that transfers winning strategies of one to the other?
I don't know. No, I don't know of anything quite like that. I mean, this sounds. It seems there should be some. There should.
I mean, you saw it for this particular case.
Yeah. Yeah. That's a good question. Yeah. Yeah, Bartek.
So the graph, or the system of equations that you construct from a toroidal graph like this,
Yes.
is almost ordered. Because if you put an order on the toroidal graph
Yeah.
itself,
Yeah.
then it's
That's
an
right.
ordered structure of a small unordered pattern.
Exactly. Yes.
So it seems like we're still just scratching the surface of the problem, because it's still a very easy counterexample.
No, this is right, and in fact, Cypher and Immerman in their original proof point out this fact that this thing has what they call bounded color class size, right? So there's a way of coloring, a definable coloring, in fact, of this, where the size of each color class is bounded by about 3 or 4. 4. No, in fact, you can't do 3.
Do
But
we have any idea about constructing properly difficult examples of graphs?
yeah, now that's a very good. Okay, well,
What would you consider properly difficult? In which sense? Because, I mean, if we had a graph canonization algorithm for in polynomial time, then the whole thing would,
but I mean, I think there is something here. I think there's something to what Bartek is saying in the sense. There are some results. I think Lipkin and somebody on what they call almost ordered graphs, structures which, I mean, are even more almost ordered than this, in the sense that there's a linear order, except on some logarithmic number of elements where you have a pre-order with at most 2 or 3, and they show that a lot of capturing results which work on ordered graphs fail, rather badly, with just, if allow, with this minimal amount of non-order. So the boundary between ordered and unordered is sharp in that sense.
One thing that happens to be the case is that so this structure can be represented as a graph where these unordered bits contain 6 nodes.
Yeah.
You can prove that it's the minimum. I mean, if the patches are
4.
size
4.
FPC is still plus counting is still okay.
No, I think, I don't know, but maybe for these particular graphs, but in general, FPC can express all polynomial time properties on graphs with color class size 3, but already on 4 it fails. You can construct examples with color class size 4 where it fails. Yeah. Okay.
But the interesting new results on choices polynomial time capturing certain of these bounded color class cases where you have an abelian
abelian structure on the color classes. That's right. That's right.
So in that direction, one has come quite a bit further.
Okay, I think we should stop here and take a break.